about too much anymore on the course, and proton NMR. Empirical formulae data have been given for us. So from that, again, if anyone needed reminding, we take the percentage, divide it by the AR of the element to get a ratio, and then divide all of those by the smallest of the values. That fixes one of them as 1, and in this case, you'll then get the empirical formula C2H6O. Now let's just get the mass spectrum out of the way first. That's the empirical formula, the simplest whole number ratio of each type of element in the compound. That might also be the molecular formula. The way to check what's the MR of the empirical formula, well, it's 46. The only thing we can take from a mass spectrum is the MR of the substance. The peak furthest to the right on the mass spectrum, which is the one in the middle, is what we call the molecular ion peak. That's basically the molecule plus having landed at the detector and been detected. So the MR is also 46. Therefore, the empirical formula is the molecular formula. So in other words, we're dealing with a compound that actually has the formula C2H6O rather than just the EF of that. It could have been C4H12O2, but that wouldn't add up with it, the MR being 46. Anyway, so conclusion, there's 1 oxygen and 6 hydrogens. That's useful for the other bits. There's an O. Now, if we think about what we know about functional groups, there's a good chance that O is either a carbonyl or an OH. It can't be an ester or a carboxylic acid because there's only 1 O in the formula, so that knocks those two out of contention. It could be an ether. Ethers are not a functional group we study the chemistry of, but they do pop up as examples in spectroscopy. It could be that, possibly, so that's something to be cautious about. But anyway, we don't need to think too hard about it. There's a massive OH absorption there. It can only be OH alcohol because there's only 1 O, so it couldn't have been a carboxylic acid because then we'd have had the carbonyl and 2 O's in the formula. But anyway, there it is. So we've got an OH alcohol. If that peak was to the right of 3000, that would have been OH acid, which wouldn't have made sense here, as I say, with that 1 oxygen. So we've found our O, it's an OH. So now the proton NMR, we can hopefully piece this together a little bit. Only 2 carbons, 6 hydrogens, MR's 46. It's ethanol, by the way. Now we know that there's an OH in there, and this singlet integration 1 has got to be that OH hydrogen then. We know that there's one there, we've added that up already. So there it is. So now I look, oh, by the way, I should have said the integrations are noted down there. We can see we've got this quartet integration 2 and this triplet integration 3. And again, just to be sharp about it, we should be thinking about the possibility that they are an ethyl group, because that's a classic pattern. Quartet 2 and triplet 3, that's an ethyl group. CH2 next to 3 and CH3 next to 2. So the 2 is a quartet, it's next to 3. The integration 3 is a triplet, and it's next to 2. So those give us a CH2, CH3 group. We've just accounted for both carbons and 5 of the hydrogens. The only way we can stick these 2 fragments together now then, the ethyl and the OH, is to have ethanol, which is our correct answer for this one. Also, just to observe, a bit of a reminder, OH hydrogens don't do splitting, as in they don't get split by their neighbours. So this H, the OH, is a singlet rather than a triplet. It is next to that CH2, but we don't count that for splitting, nor does the OH have any impact on the splitting of the CH2 signal. So the integration 2 peak is getting split into a quartet because it's next to 3 on that side, nothing to do with the OH on the other side. So that one's ethanol. This projection's a bit laggy, so let's hope the recording comes off all right. Okay, next one, again, the empirical formula's been done for us. Take those, divide by the ARs, divide by the smallest, make it a whole number ratio. You get C4H8O here. Has anyone got the MR for C4H8O to hand? Just shout it out if you've got it. 70, I'll take it. 72, yeah. Fine, sensible looking number without counting it carefully. And again, like we did before, the mass spectrum, the peak furthest to the right is the MR of the substance. Once again then, it's looking like the empirical formula, which we've got from the percentage composition there, is the molecular formula. It won't always be that way for all those questions. That's fine, yeah. How can I tell? I'm glad you've asked. We've got the empirical formula by doing these percentages over the ARs and so forth, right? That's just the simplest whole number ratio of C to H to O in this compound. the MR of the empirical formula is 72. The MR of the compound is 72. So all you're getting from a mass spectrum is the biggest M over Z peak is the MR of the substance. Thanks for that. Okay?
So would you still get the total MR and just times it by the percentage and then...
take the MR and multiply it by the percentage H.
In this case, if you times 72 by 2/3, you get 48 in it. 48 divided by 32 plus 4, you know, 4 carbons.
I'm not quite following that. Ask me at the end if you don't mind. Right. Okay, we'll keep on this thread for now, but possibly. Now, that's given us the fact then that there's 4 C's, importantly 8 H's, we'll look at the NMR spectrum in a minute, and 1 O. Again, there's only 1 O, so this can't be a carboxylic acid or an ester or anything that has 2 O's in it, because there's 1. So let's quickly jump onto the infrared. No OH for alcohol, no OH acid, wouldn't make sense. Classic signature signal at about 1700 wave numbers there for carbonyl. So this is looking like it's an aldehyde or a ketone then. Now let's decide which based on the splitting in the NMR spectrum. So we've got a 4-carbon substance that contains a carbonyl. So we've got 1 carbon, the oxygen accounted for already. Let's have a look at this. The integrations are given down there, 2 to 3 to 3. Let's deal with this integration 3 singlet first. The fact that it's a singlet means that there's no hydrogen on the adjacent carbon. And we do know there's a carbonyl in this structure somewhere. Come back to that in a second. The integration 2 and integration 3, quartet and triplet respectively, again, same as what we saw before, that just screams ethyl group at us. If there's a triplet and a quartet and nothing else, or only singlets other than that, they must be together because they're splitting each other. So that's going to be an ethyl group. We need to do more though. So we've spotted that the CH2 integration 2 is a quartet because it's next to 3. The CH3 integration 3 is a triplet because it's next to 2. We need to just double check the shifts here. Now both of these peaks, the ones furthest to the left on the NMR spectrum, are up in the region which would suggest that they are representing hydrogens on a carbon adjacent to a carbonyl. And that's true for both. So I suggest that what we have here is a CH3 next to our carbonyl. So there's the singlet peak sorted, no adjacent non-equivalent hydrogens, integration 3. And the shift matching that. And then on the other side, we've got the other 2 carbons and the rest of the hydrogen that we found in the formula. So that must be the CH2, CH3, where the CH2 is giving us this integration 2 quartet. The shift suggests it's a hydrogen on a carbon next to a carbonyl. It's on like the other side of that carbonyl, so the singlet we found. And then the other integration 3 triplet is in the RCH3 environment, suggesting it's just next to alkyl hydrogen, which is next to the carbonyl, but we're going next door but 1 there. So there it is, it's a ketone, we've got butanone. Now, if you found you had butanal, then you'd find that the NMR spectrum doesn't match. This is the incorrect answer, I'll have to scribble it out in a minute. But if we had butanal, that would account for the carbonyl appearing in the infrared spectrum. It's a structural isomer of butanone, so it does have the same molecular formula and empirical formula and MR. Problem is, oh look, and we would have a singlet integration 1 there, but we don't have that in this. We've got a singlet integration 3, so it couldn't have been this. And also this CH2 in the middle of butanal's main chain is adjacent to, well, more than 3 hydrogens, so that would be more than a quartet, which is the biggest splitting pattern we've got there. So there's a few reasons why it couldn't possibly have been butanal, which is an answer we saw around the classroom a couple of times. On to number 3. I really hope this video holds up, it's a bit laggy. So C3H6O, we work out, is the empirical formula for that. Let's just double check the MR of C3H6O, so that's 3 12s plus 6 plus 16, adds up to 58, okay, if I can count. So the MR of the empirical formula is 58, and again, sure enough, that's the MR of this actual compound. So yet again, the empirical formula is the molecular formula. The empirical formula is always like you can have integer multiples of that to get the molecular formula, but it is actually that in this case. So we've got C3H6O to work with. Once again, we've got 1O. And so I'm thinking alcohol or carbonyl are the most likely. It could be that ether, COC bridge. There's no alcohol. Oh, yet again, another signature that we should go in looking for. Around 1700 wave numbers, we've got a carbonyl stretch there, okay? Now, if you're ever having to justify this in a more wordy way, like in an exam style, always put the wave number down. So I would say there is a peak at 1700 Cn-1, which indicates the presence of a C double bond O. So write the type of bond out and put what wave number it's appearing at, or it's centered on. So we've got a carbonyl here. It's C3H6O, so there's not a lot more to say. We go and have a look. It appears that at the NMR spectrum, all 6 hydrogens are in the same environment. To be honest, you wouldn't get an integration of 6 when there are no other peaks to compare it with, because it's all about relative peak area, and there's only one peak here. TMS is a separate matter. So actually it doesn't have integration 6. It has no integration because there's nothing to compare it with. There's one peak, which means there's one environment, which means that both carbons and therefore all 6 hydrogens have to be in the same environment as each other for this to work, basically. So this must be propanone, and I'm not going to say any more than that about that now. So that must be CH3COCH3. On to the next one, number 4. Okay, right, so this time we've got an empirical formula that we probably do need to think a bit harder about. We've worked it out, again, in advance of doing this answers, to be CH2O. So the MR, I shouldn't have to use a calculator for this really. The MR of the empirical formula, CH2O, adds up to 30. Let's just quickly check the MR of the actual substance. The heaviest mass peak on the mass spectrum tells me that actually it has an MR of 60. So what we have here, the molecular formula, is 2 lots of the empirical formula. So the ratio of C to H2O in this compound is 1 to 2 to 1, but actually this must be C2H4O2. So we finally had to do something other than just copy the empirical formula here. Remember that the empirical formula goes into the molecular formula an integer multiple of times. So C2H4O2, to be honest, the options are pretty limited here as to what this might be. We've only got 2 carbons to play with. We could probably draw all the structures of C2H4O2 out and see what we get. I'm just going to throw a bit of a curveball out there. It's not something I'd expect people to be thinking of automatically. The C to H ratio here is Cn to H2n. Now that says to me it's once unsaturated. If it was saturated, single bonds only, it'd be CnH2n plus 2, because O's kind of slot in between C's and H's if they're alcohols. This is once unsaturated. Now it can't be a ring. Well, it could be a ring actually, because C's and O's can both have double bonds. We're looking at something that's got 1 double bond in it. Let's not waffle too much though. Let's look at the NMR spectrum. There's a real signature move here, and then we can double check the infrared to check it agrees. Remarkably, we've got this peak all the way up. Integration 1 way up at 11 or 12 there. Now that suggests to me, again without looking at table C, either an aldehyde, hydrogen, or a carboxylic acid, hydrogen, and that's without being careful enough to just look at table B and check which one it is. Now there are 2 oxygens in this formula, so let's go digging a little bit and see what we can find. There's obviously also this CH3 here. There are integration 3 suggests it's CH3 here. We've only got 4 carbons in total, sorry, 4 hydrogens in total, 3 to 1, so that's the actual number. No non-equivalence, and it's up at a shift of 2 point something to hydrogen on a carbon. Happen. Before we look at the infrared to confirm something. Were by single end, I'm just trying to make a point. And then if it were an aldehyde, which it isn't, then I'd need to just have noticed some is a characteristic of an alcohol. We need to clarify that, and that's definitely peak once again. Let's come back to this in a second. then that might have purposely not looked at table B and check the shift on it. Though there's only space for two H's, so I have got C2H4O2 there, but the NMR spectrum doesn't match that. Okay, I've got this singlet integration one. Don't have three equivalent hydrogens, can't be correct. Anyway, so it must be ethanoic acid. Equivalent hydrogens. We do indeed have the carbonyl, and this actually must be OH brackets acid, even though when we look at that, it appears to me to be centered to the left of 3000, which is best match from table B would be, table A, infrared spectral data would be OH alcohol. Formula is C2H4. We'll check it as always. Whoops. Again, I didn't really need a calculator for this. Or did I? The empirical formulas MR weighs in at 44. Absolutely nothing to indicate alcohol or acid, so that's a dead end. Definitely got this carbonyl signal there, which is telling us that, well, it's got a C double bond O in it. Could be a diketone, keto ether, could be all sorts of weird stuff. We better get this one done quite quickly now, though. NMR. We know that there are 8 hydrogens in the formula. Group. It's the only possibility. There's many other split peaks as well. With that in mind, this singlet integration 3 is a CH3 adjacent to something else, which doesn't have hydrogen on it. Right, let's cut through this now. We know there's a carbon group signal. That's the singlet which is next to a carbonyl. The shift tells me it's next to a carbonyl. After that, there must be a single bond O in there. My only indication of that is that there are 2 O's in the formula. There's nothing interesting going on with the infrared spectrum, potentially. There might have been something actually. And the shift, this quartet integration 2, the shift of it is not next to a carbonyl, it's further to the left than that. So this must be our CH2, finish because it's lesson time as well. Couldn't have been this. was a methyl ester rather than ester, then that singlet integration 3 wouldn't have had a shift of 2 something, it'd have been more like 4 point something. So actually what it came down to here, the deal breaker was the shifts on the things that were attached to oxygen. Anyway, let me scribble that one out. Let me just confirm that ethyl ethanate was the correct answer there. There you go. Hope that's of some use to some of you. Cheers, folks.